In this video, I'm going to describe how to simulate the performance of pressure swing dryers using Pedco's Adsorptive gas dryer simulation software. If this is your first experience with the Pedco Adsorptive gas dryer simulation software, it's recommended that you view the overview video first. When the program is launched, it'll open with a form that has the dryer type selection. You'll note on this form that there's 3 different types of dryers that can be simulated, including thermal swing, pressure swing, or once through or non-regenerative type dryers. The focus of this video is going to be on the pressure swing type dryers. I'm going to start with the conventional pressure swing. So if I click on the conventional pressure swing and I hit select, we'll be directed to a form that has a flow diagram for this conventional pressure swing dryer. The conventional pressure swing dryers are a dual tower type system. You have one drying tower and a reactivation tower at all times. The piping network that directs the flow from between the 2 towers. In this case, we're showing inlet air coming into a 4-way valve. The 4-way valve directs it to the drying tower. The air flows through the desiccant in the drying tower where the dew point's reduced. The air goes to the outlet 4-way valve. The 4-way valve directs it to the outlet to the point of use. A portion of the dried process gas is pulled off. It's run through a flow control device through the 4-way valve. It flows in a direction through the reactivation tower, which is counter to the drying flow direction, down through the desiccant, desorbing water. That air is directed to the 4-way valve, which directs it to a muffler, and it's exhausted to atmospheric pressure. The dryer will operate in a mode like this for half of the cycle. So if it's a 10-minute cycle, the drying tower will operate for 5 minutes. The reactivation will occur over a 5-minute period of time, which would include depressurization, purging, and then finally repressurization. At the end of the reactivation, the 4-way valves would switch position. The reactivation tower would then be drying the air, and the drying tower would be reactivating the air. And then we would continue cycling back and forth continuously as long as there's a demand for dry air. Now I'm going to go back to I'm going to click on New Selection. I'm going to go back to the dryer type window and briefly explain the difference between the conventional pressure swing dryer and the vacuum purge, and then finally the single tower dryer. The vacuum purge, if I click on vacuum purge and hit select, again we're directed to a flow diagram for the vacuum purge dryer. You'll note that it's very similar to the conventional pressure swing dryer, with the exception that there's a vacuum pump on the purge outlet. What this does is it enables regeneration in the reactivation tower to occur at a reduced pressure, subatmospheric pressure, typically somewhere in the neighborhood of 3 to 5 psia. The benefit of this, it allows you to reduce the amount of purge that's required to achieve a specific dew point. For instance, you might be able to reduce your purge requirement from 15% to 3 to 4% by including the vacuum pump or an inductor. I'm going to go back to the dryer type window again by clicking on New Selections, and we're going to talk briefly about the single tower dryer. So we click single tower and hit select, and again we're directed to a form that has a flow diagram for the single tower pressure swing dryer. Air comes in the bottom upward through the desiccant vessel, through the desiccant bed, through a check valve, you'll have a purge volume on the outlet end of the dryer, and through another second check valve to the compressed air demand system. When the compressor that this dryer is tied to unloads and stops pumping air, at that point your purge valve would open. The desiccant would be regenerated by this purge volume of air that would flow countercurrent first through this purge orifice and then through the desiccant bed and then through the muffler and out into the atmosphere. As far as the physics are concerned, there's no difference in the 3 types of these dryers. It's just a matter of the actual pressure condition that the regeneration is accomplished under. So I'm going to click on the New Selection again, and we're going to go back to the dryer type window, and at this point we're not going to keep backtracking. I'm going to talk about the conventional pressure swing dryer, and we'll follow through all the way to explaining the output that you get from this simulation. So conventional pressure swing dryer, we click on select, We go to the flow diagram where we were before. I'm going to click on the default values button. The default values button is going to populate all the data input fields with a consistent set of data. For the purpose of this tutorial, I'm going to use the default values rather than spend a lot of time entering different information. So let's look at the operating conditions. On the drying side, we're running a simulation for a dryer that can treat 350 SCFM of air at 100 degrees Fahrenheit, 100 pounds pressure, on a 100 degree dew point, which means it's saturated. We're going to be running a 10-minute cycle, so we have 5 minutes available for drying, and we're going to have roughly 4 minutes available for the actual stripping or purging. This gives us a minute available for the depressurization and the repressurization. Additional data that's necessary here, the vessel data. We have a vessel that's 12 3/4 OD, 12-inch ID, so the desiccant bed's 12 inches in diameter. The length of the vessel, at least the effective length of the vessel, is 60 inches. And really what this means is you have a 60-inch bed of desiccant material. An R value of 0.5, this is a good resistance to heat transfer to the ambient, which is all you're interested in a pressure swing dryer. The specific heat of the vessel material and the density of the vessel material. Continuing ambient conditions, we're simulating ambient conditions at 100 degrees Fahrenheit and 14.7 psia, standard sea level pressure. The initial bed conditions for the desiccant. The desiccant has an initial moisture loading that's such that at 100 degree Fahrenheit temperature, it's capable of producing a minus 40 degree dew point. Also, you'll see the number of cycles we're going to simulate here. We're going to simulate 576 cycles, and 576 cycles with a 10-minute cycle time, that's going to give us 4 days of simulation. And with pressure swing dryers, things change very slowly, and it's important to simulate many days of operation to really know how the dryer is going to perform. I'm going to click on select desiccants, and here click the default values just so we can see the desiccant type that's going to be used. And in this case, we're going to use activated alumina, 1/8-inch diameter. That's a very common desiccant for industrial compressed air dryers. If we click on OK, I'm going to click the run, and those of you that have seen the overview video will realize that we're going to get a number of warnings here that's telling us no output control data was specified. You want to use the default values, and I'm going to say yes. No numerical system data was specified. You want to use the default values. I'm going to say yes. No transport coefficient data was specified. You want to use the default values. I'm going to say yes. And at that point, it launched Excel, and you'll see that because I've done this run before, when you launch Excel, it sets up a file name that's much like a model number for the dryer, and it has to save this in and since I already have a file with that name, it's telling me that I want to replace it. I'm going to say yes, and at that point it launches Excel, and it's setting up the workbook with all the sheets that have the information about this specific run. So everything's self-contained in one Excel file. Again, there's a sheet that has the input data for the run. There's the most important sheet here is the plots. What I'll do is I'll pause this video and come back and explain the information that's provided on the plot sheet. This particular run is going to take about 12 minutes on this computer. The pressure swing dryer runs, we're simulating 4 days of operation, so it does take a reasonable amount of time. So with that, I'm going to click on the pause, and then I'll come back when this simulation is completed and describe the output that we're getting. So the simulation is completed now, and what we're looking at is the plot sheet in the Excel workbook. And on the plot sheet, we have 3 charts. We have a chart that shows dew point, a chart that shows the desiccant loading in pounds of water per pound of desiccant, and one that shows the temperature. And these are all plotted as a function of time, 0 to 96 hours or 4 days. As you recall from the input data sheet, we had 576 cycles, which gave us 96 hours or 4 days. If we look, there's 5 lines on each one of these charts. The black diamonds are the drying inlet, the magenta squares are the quarter of the way through the desiccant, the red triangles are halfway through, and these are positions from the drying inlet. The blue X's are 3/4 of the way through, and the green asterisks are on the drying outlet end of the bed. One of the unique things about these plots is you see this sawtooth type characteristic. Because we're only simulating one of the desiccant beds, what we see initially is the dew point that occurs at the end of the drying, and then the dew point at the end of the regeneration. And this would be at 2 hours. So then the dew point at the end of the drying at 4 hours, and at the end of the regeneration at normally 4 hours as you go through. So it takes a little bit of just studying these to appreciate what's actually being plotted. So what you're interested in as far as the dew point coming out of the dryer is the values at the peak, the higher values here on the dryer, on the drying outlet end of the bed. Another very useful sheet here has detailed output, and if I click on the detailed output, what you'll see is it gives you a cycle number, 144 cycles, and the total time, and the cycle time in the particular cycle that we're looking at. And this is going to be a snapshot of the conditions through the bed. And what I'm going to do is I'm going to scroll down here to towards the end, the last cycle that was simulated, and I'm going to go to the 5-minute period of time. So this is 576 cycles, so this is the last cycle. This is the end of the drying. We're still running the 350 SCFM. As you look distance from the inlet from 0 to 60 inches, we see things like bed temperature, loading, velocities. Velocities in this dryer we're running about 60 feet per minute, which is a very typical velocity. You're comfortably away from issues with fluidization, but not far enough that you have a much bigger diameter vessel than is required. It's interesting to look at the bed temperatures and see what's happening, because people talk about heatless dryers, and the truth of the matter is there's a lot of heat exchange going on in these desiccant beds. You're coming in at 100 degrees and you see the temperature climbs to about 110 because of the heat of adsorption, and then it drops back down to about 103 on the outlet end. It's also worth taking a look here at the 9-minute point. Okay, so this is the end of the regeneration. And if we look at the bed temperature again, you're on the drying inlet end of the bed, we're somewhere around 100 degrees, and the outlet we've cooled down to about 90. So this is the heat that's required to desorb the water comes from the sensible heat of the desiccant, and consequently what happens is that you see the temperature of the desiccant drop. So it's very important that beds are sized large enough so that you can store the heat of adsorption, so that it minimizes the amount of purge air that's required. And it's very easy with this simulation to see what happens if you, for instance, reduce or increase the amount of purge, and not only on the importance on the dew point performance, but also what happens as far as the temperatures in the bed. Not that that's necessarily something that the customer is concerned about, but that the dryer engineer that improves his understanding of the physics of what's occurring. We click back to the plot sheet, and just one other thing I'll highlight here, the plot data. If you want to see the numerical values, if you click on the dependent variable versus time sheet, it'll actually give you the numerical values that are plotted. So if we scroll to the bottom here at 96 hours, or 95.92 hours would be the end of the last drying cycle, we're achieving only a minus 11 degree dew point from this dryer. You can see what the desiccant loadings are. The inlet end, the desiccant loading is about 39%, which is pushing the maximum capacity of activated alumina. On the dry end of the bed, we're somewhere down around 2%. So at 2%, we're achieving this minus 11 degree dew point. So with that, this concludes the demonstration of using Pedco's adsorptive gas dryer simulation software to simulate pressure swing dryers. Thank you.